My dear friends, welcome to Rajashekhar classes on applied data science with Python. This is lecture number 615. In this lecture, I will continue my discussion on convolution layers in Keras. Just let me show this particular website. Just say this one once. What is this? Yes, this one is related to available initializers. I request all of you to go through this particular document. What are the available initializers, random normal class, Keras dot initializer, so dot random normal, mean equal 0, standard deviation equal 0.05. Just I request all of you to go through this particular documentation, random uniform class, their code examples, and what is max value, what is min value, what is the seed, and what is this truncated normal class, what are the different arguments, what is the 0 class, what is the 1 class, just all these example. Glorot normal class, isn't it? Glorot uniform class, their particular examples. Hey normal, we already discussed hey normal, isn't it? Hey normal class. Just see this particular documentation. Just see regularization layers, dropout layer, spatial dropout layer. For example, if I click actively regularization layers, L1 regularization factor, isn't it? L2 regularization, we already discussed. Just see this one, pooling layer, convolution layer, core layers, isn't it? Pre-processing layers, recurrent layers. Just I request all of you to go through this particular document. Just see this one, keras.layers.con. Today you have kernel initializers, isn't it? So if you want to know what initializers available for kernel, here kernel initializer, by default what it's right, Glorot uniform. I already discussed about what is Glorot uniform. Kernel initializer for the convolution kernel. If none, the default initializer is Glorot uniform will be used, isn't it? These are available initializers. This we have seen few seconds back, random normal class, isn't it? Keras dot initializers dot random normal class, mean equal 0.0, standard deviation equal 0.05, isn't it? In similar manner, I have something like random normal mean equal 0.0, standard deviation equal to 1. That is random normal initializer, isn't it? There are different types of initializers. In similar manner, random uniform initializer, isn't it? Min value equal 0.05 and max value equal 0.05. You can have 0 class, you can have 1 class, isn't it? Class dot initializers. You can have keras dot initializers dot glorot normal, keras dot initializers dot hey normal, isn't it? Active regularization layers, L1 regularization, L2 regularization. Just if you recall, actually what is the purpose of regularization is an important concept for neural networks, as it provides, what it provides, it prevents neural networks from overfitting the training data, isn't it? It increases the generalization capability of the neural network, and it improves overall performance of the neural networks. Regularization techniques for neural networks, just I request all of you to go through this particular slide. Weight or parameter regularization, that is category 1. Neural network specific regularization, that is category 2. Other methods, that is category 3, isn't it? In category 1, that is weight or parameter regularization, you have L1 regularization, L2 regularization, neural network specific dropout regularization comes under category 2. Early stopping, data augmentation, I already discussed about data augmentation, adding noise, all these things will comes under category 3, isn't it? Just see this one, you have as I discussed, these are initializers that readily available. We have seen in different initializers. Imagine amount of code that we are writing, literally we are defining in one line of code. Similarly, if you want to know what type of regularizers, isn't it? We already discussed about initializers. Similarly, if you want to know about regularizers available, just go to regularizers. Just see, we have seen just L1 regularization, L2 regularizer, isn't it? All types of regularizers. You can easily add regularizers the way you want. Here just adding regularizer is very simple, isn't it? So so here I am adding what is this, just say regularizer dot, what it is, says regularizer dot L1 of 0.01. what is this L1? It is something like lambda. Here lambda equal to 0.01 regularizer, and again regularizer dot L2 of 0.01 means we discuss something like lambda L1, lambda L2. Just try to recall our previous class. This coefficient, this 0.01, this is a coefficient of regularizers, that is lambda L1. Lambda is a coefficient of regularizer. Lambda times lambda L2, lambda times L2 regularizer. Similarly, you can add L1 regularizers. Even adding regularization is extremely simple, isn't it? Adding regularization is very simple here. What you have, what you really love about Keras is it is literally in one line of code. You can define, let's lots of if you can define whole structure in one line of code. This is how convolutional layer can be defined. Now let's go to this is convolution layer. Let's go to max pooling layer. Max pooling layer is much simpler. You basically have pool size. Just try to recall, we discussed max pooling layer. What you have to do, you have basically have the pool size, oftentimes these numbers, pool size equal to 2 comma 2, and we already discussed what is pool, isn't it? If you want to have strides, you can have strides. I already discussed what is strides in my previous lectures. What type of padding do you want? Very simple. Max pooling anyway is basically the pool size, and here you have pool size and stride, isn't it? And what type of padding you want? Very simple, isn't it? What type of padding you want? The third thing, very important function is flatten, isn't it? Let me explain what flatten does. Imagine I'm trying to build simple convolutional model here. I think it is easy to explain with example. Imagine I have a con 2D, isn't it? Just see here, flatten the input does not affect the batch size, isn't it? Flatten the input does not affect the batch size. That's the important point, isn't it? Just see how you write model dot add con 2D 64 comma 3 comma 3 border underscore mode equal to same input size, what is this input shape 3 comma 3 comma 32 comma 32. What does it mean? I have con 2D 64 60. What is this 64? This 64 kernels of size 3 by 3. There is 64 comma 3 comma 3 means there are 64 kernels whose size is 3 comma 3. Border equal to mode or padding. Border or padding, they are of same meaning. We can write either of them. You can write border, or I can write border underscore mode or padding. We can write either of them. Either of them means either you can write border underscore mode or I can write padding. And the input size is, what is the border underscore mode or padding are same. The input size is, what is the input size? 3 comma 32 comma 32. We are doing same padding. You have 3 by 3 kernels. You have 3 by 3 kernels. You have 64 kernels or 64 filters. I can say you have 64 kernels or 64 filters. The output, what is the input shape is 3 comma 3 comma 32. The output is going to 64. What is this? Output is going to 64 into 32 into 32. Isn't it? You have 32 by 32 image, isn't it? Your input shape is 32 by 32. Just see there, input shape 3 comma 32 comma 32. 32 into 32, you have 32 by 32 image, because input size is 32 by 32, isn't it? Or input size is 32 by 30, and you are using same padding, isn't it? Border underscore mode or padding, they are of same meaning. What you are writing here, you are writing same. Just see border underscore mode equals same. What does it mean? You are using same padding. This 64, what is this 64? This 64 is basically is basically number of filters. This 30 by 32 is just like n by n, isn't it? Just 64 is 64, what is the, I will repeat, 64 is basically number of filters, isn't it? 32 by 32 is just like n cross n. Basically, you have a 3D tensor, isn't it? What is this? 64 into 32 into 32, that is 3D tensor, which is of the size 64 into, what is the size of 3D tensor? 64 into 32 into 32. Let me write it down here. So you have 3D tensor which is of size 64 into 32 into 32. When I apply flatten operation, on top of it, what it does is, think of this as a cube, isn't it? Think as a cube of data. You have 32 here. Just if you observe here, this is 64 by 64. What is the meaning of this one? Just see here. This 32 by 32. Just see, this is 32. This is 32, isn't it? What is its depth? Its depth is 64, isn't it? That's what it says. If I apply flatten operation on top of it, what it does is, think of this as a cube. This is 64 into 32 into 32. Just you can think of it as it's a cube. You have 32 here. 64 into 32 into 32 means what? Here you have 32 here. You have 32 here, isn't it? What is the depth of this one? Your depth of this one is 64. Basically, you have the cube of the data. You have three-dimensional matrix of data, isn't it? You have three-dimensional matrix of data. Flatten basically converts this into one-dimensional array, isn't it? It converts into one-dimensional array. And how many values are present here? Total number of values are 64 into 32 into 32. You have 64 into 32 into 32 values. When you flatten this data, these are the total number of values. What are the total number of values? 64 into 32 into 32. You have total number of values. You have how many values you have? 64 into 32 into 32. Because this is cuboid of data, this is a 3D array of data. When I flatten it, what I will get is basically one-dimensional tensor. Just see, flatten basically converts 3D tensor into one-dimensional tensor. Just if I flatten it, I will get one-dimensional tensor of size 64 into 32 into 32, that is essentially 65,536. Flatten basically converts 3D tensor into one-dimensional tensor. What is its size? 64 into 32 into 32, isn't it? Just try to recall our M. Just see this one. Just we are keeping all these values. Actually, in 3D tensor, I am keeping values. First, I am copying all these values like this. Just understand this one. Just I am copying these values like this. This first value, again second value, again third value. Just like each and every value I am copying one after the other, isn't it? For example, if you take what is this MNIST data set, where you have each image of size 28 by 28. If I flatten it 28 into 28, I will get 784 dimensions. So this flatten operation, what is your input size? Your input size is 2D tensor and output size is 1D tensor. This is what we did in MNIST data set, isn't it? We converted 2D vector into 1D vector in MNIST data set. So these three are the most popular operations, isn't it? So these three are most used operations. Now let's go back to the example that we have seen, isn't it? This is the example which we have seen. So we understand what we understand. We understand convolution layer. You have 20 filters or kernels. Kernel size is 20, 5, 5. Kernel size is 5 cross 5, isn't it? The border underscore mode or padding is same, which means just the input border underscore mode we are keeping same. Same means what? Here 20 comma 5 comma 5 means what? You have 20 filters or 20 kernels. Each kernel size is 5 cross 5. In border underscore mode or padding is same. If I write border underscore mode equals same, what is the meaning? Input and output size is same, isn't it? Just if you observe carefully, with I can say I am also mentioning input size, isn't it? It is always recommended to give input size, especially for the first layer, isn't it? For the first layer, the code is tried significantly optimized. Then I'm doing max pooling, isn't it? Just the input shape equal to depth comma height comma weight, isn't it? You are mentioning input size. Why you have to mention input size? It is, that's what we are discussing. I am also mentioning the input size. It is always recommended to give input size, especially for the first layer. The code is significantly optimized. Then I am doing max pooling. Pool size is, what is this max pooling? Max pooling pool size is 2 cross 2, and stride is also 2 cross 2. So I already discussed what is pool size, what is stride, all these things. So here I have flatten operation, isn't it? What it did, flatten operation, it is just see here, model dot add flatten, isn't it? Here I have flatten operation. Whatever 3D tensor here is converted into, here by using your flatten operation, your 3D tensor will be converted into 1D tensor, isn't it? That's what it says. And then I have dense layer. Just see, I have dense layer here and soft max layer. You can have soft max layer. Actually, it is related to MNIS dataset. It is 10 class classifier. I hope this simple code gives you a flavor of how to implement convolutional neural networks in Keras. We will see more and more code in Keras, more and more convolutional neural networks like AlexNet, like VGG. These are very, very popular, just like LeNet. LeNet is I can say LeNet is older version, and it is maybe 98 version. There are more recent versions since 2012. I think VGG is in 2014. The bunch of more recent neural networks, we will understand the architectures of all of them, both visually as well as in Keras code, isn't it? Because nothing beats code. Code gives you a cleanest idea of network architecture. I request all of you to go through this lecture. If you have any difficulty, please keep a comment. Thank you very much.